Hey everyone, so we're going to continue our discussion with forces, but we're going to switch a little bit off to a slightly different concept, the next unit, which is all about circular motion and gravitational forces. You can think of this as almost special cases with forces. We still will end up using Newton's laws, uh, but it's going to be applied to very specific scenarios. All right, so we're starting with circular motion, and in particular, uh, I want to point out the fact that we are once again returning to the idea of objects moving in two dimensions. So if you recall, the last time we talked about this was when we did projectile motions. When objects move in one dimension, essentially what's going on is the acceleration and velocity are within the same plane. Now we're going to end up having a scenario where, just like with projectile motion, the velocity and acceleration will be in different planes. So one's going to be horizontal, the other one's going to be vertical. Um, this ends up resulting in objects moving in circular motion, which is moving in a circle. Easy enough. One thing I do want to point out is some of the stuff that I'm going to mention in here will seem to contradict your own perception. A lot of times when you do the problems in physics, you should be able to kind of visualize and almost imagine yourself in certain scenarios. For example, the elevator question that we did in the previous unit, you should be able to, imagine yourself in an elevator and the feeling that you'd get. If you try to do that with circular motion, though, it can get a little bit contradictory. You'll see what I mean in a bit. All right. So we're going to actually start off with the very simple case of objects moving in horizontal circles and moving at a constant speed. We're going to call this uniform circular motion, but later on we will actually talk about cases where the speed is not constant, where maybe instead of being a horizontal circle to vertical circle, but we'll cover that later on. That's actually going to be in the third part of this overall unit. So for now, we're just going to focus on the simpler cases. Now, my main question here is an object that's moving in circular motion, in this uniform circular motion, would this be in equilibrium? I do mention that it's moving at a constant speed. And you might think, well, yeah, because Newton's first law says moving at a constant speed should be in equilibrium. However, it's important to remember that there is one small detail in that statement. Newton's first law says for every when an object in motion tends to stay in motion, moving in a straight line. So, because the object is actually changing direction, this object actually is accelerating. Recall that it's all about the change in whether or not the velocity changes. So if the velocity remains constant, then your object's in equilibrium. The speed doesn't really matter. It's all about the velocity. So, if you're moving in a circle, you're always accelerating. Now, we need to figure out what direction this is. So, there's a few ways to think about it. First, if we have an object moving in a circle, we can figure out the velocity by drawing lines tangent to the circle. Now, the reason it's like this is because, again, Newton's first law. An object in motion tends to stay in motion, moving in a straight line. An object would be moving in the circle and accelerating, but if at this point it gets released, it'll go in a straight line. Similarly, if I release it over here, it goes in a straight line tangent to that circle. Um, so now the question is, what is the direction of the acceleration? Now, you don't need to actually do this. This is something that you might end up seeing later on in like college classes when it comes to vectors. So normally, if you remember, when we take vectors, we can only really combine vectors of the same type. Taking a force with another force and adding them together, or taking a force, well, two forces and then subtracting them, having them at angles, whatever. But it turns out that we actually can use velocity vectors in order to determine acceleration as far as direction's concerned. The way we end up doing this is we start with the equation for acceleration. Acceleration was the change in velocity, v minus v naught over t. So what I can do is I can take my two velocities. In this case, if we go back to the previous case, velocity 1's going up and to the left, velocity 2 is going down and to the right. sorry, down and to the left. I have them over here. Now it says here that it's v minus v naught. I can actually rewrite this to be v plus negative v naught. So negative v naught would just be flipping it in the different direction. So this would actually be v plus negative v naught. And then what I can do is I can do my typical vector addition in order to figure out the general direction of acceleration. So v naught, negative v naught goes down here. I can then take v over here, redraw it so it matches exactly what I have here. And it turns out that if I drew my arrows correctly, at least, the resultant of these two will end up being the direction of the acceleration. So this whole, it's important to note that what we're doing here to find the direction is not the same as finding like the magnitude resultant like we did in previous units. But if we do a resultant vector, that resultant vector will point in the direction of acceleration. So in the case from before, the acceleration was pointed down. I could do this throughout the entire circle, picking two random points and finding the acceleration to get between those 2 points. And it turns out that the acceleration will always point towards the center. So this animation actually shows it perfectly, where the velocity will remain tangent to the circle every time it goes around, and as it goes around, the acceleration will always be pointed towards the center. We call this centripetal acceleration since it's always pointed towards the center, as in center seeking. Um, so it's important to remember this, that for an object moving in a circle, the velocity and acceleration are going to be perpendicular. Now, we've already talked about what happens when the velocity and acceleration are parallel to each other, whether they go in the same direction or opposite directions. Now we know what it's going to look like if they're perpendicular. What this actually allows me is to expand upon this and now look at cases where the acceleration and the velocity are at some angle. Now, I'll get to that later on, but I just want to point that out that if you have a perpendicular component, it will be moving in a circle. Oh, and I should also have mentioned that because the velocity and acceleration are perpendicular, that's actually what's causing the velocity to not change in value. Uh, because in order for us to have a change in value, there has to be a component pointed either in the direction or in the opposite direction. Because of perpendicular velocity and acceleration, there is no component in the same dimensions. The velocity will end up remaining constant in magnitude, the same speed. All right, so the equation that we end up having for this centripetal acceleration, pretty basic equation. It's AC equals v squared over r. You have it on the reference table, so it's not too bad. It's just plug the numbers in, chug out your answers. One thing to note is the v in this case is actually a speed, not like it really matters. Um, but one thing I want to point out is there is another equation that you're going to have to combine with this sometimes. As you've probably noticed by now, a lot of the questions that you end up seeing on the tests and the types of questions that the AP1 type likes to ask tend to focus on real life applications. Essentially, what you would expect if you were to experience these questions in a lab setting. You know, and it's very common for you not to know what the velocity is for an object moving in a circle. It's not super common for someone to be able to see something moving in a circle and say, okay, I know what that velocity is. Instead, the easy thing that you'd be able to measure and the thing that you'd be able to quickly find is the period, the time it takes for that object to move around one full trip, one full rotation, one revolution, whatever you want to call it. So we need to find a way to rewrite this equation in terms of period, things that we would be able to measure in a lab, right off the bat. So how do we find the period? Well, if you recall, speed, one of our general equations for speed is distance over time. If I think about the object moving in a circle, the object is moving along the outer edge of the circle. That distance, the length of the outer side of the circle, is their circumference. So what I can do is I can rework this equation. So instead of it being distance over time, it's circumference over time. And if I do that, then the time I can actually plug in as capital T. Period, I just want to throw this out there, that period is just another measurement of time, but it's a more special time. So it has the exact same units. It can be plugged into the into any equation with T. It's just a special time. All right. So what we can do, since the circumference is 2 pi r, we can use this equation v equals 2 pi r over t. If you want to get really fancy, you can combine this equation with the AC equals v squared over r to get another equation in terms of r and t. Again, two variables that you're most likely going to be given whenever you're dealing with circular motion. Just be careful when you if you were to do that. That only really works for in-class problems. On a test, you wouldn't be able to use that equation since it would be considered a derived equation. So here's the first question. Pause the video or work on yourself. I'll go over in a second. All right, so we're just going to plug it into the very general centripetal acceleration equation. So v squared over r. They give us the mass. That's just a red herring for us to use it since there is an equation that will use mass. But we plug the numbers in, chug out our answer, and we should have gotten 18 meters per second squared. All right, here's the next one. Pause the video, work itself. I'm going to go in a second. All right. So here, now they don't give us the speed. Instead, they give us that the amount of revolutions per second. So I'm going to have to figure out what the speed is of the object as it moves in a circle. Now, one thing I want to point out, since we're not really going to be talking about frequency for a while, so you don't really have a good way of going from this to period. I'll just mention it right now that one way that you could do it is if you ever get this revolutions per second, you could just take the inverse of this number and that will get you your period. So if you see one revolution every second, take the inverse and you'll find that you end up getting 1 second per revolution. So this ends up being your period. If you wanted to, while you wouldn't do it for this, you can set up a proportion. So let's say if this was 4 revolutions per second, you could do 4 revolutions per 1 second and set that equal to 1 revolution over x seconds. And then you cross multiply, solve for x. All right. So just throwing that out there that this 1 revolution per second isn't your period. It is in this case, but again, if that number was 4, your period wouldn't be 4. All right. So we take our equation for the speed related to period, plug the numbers in, and we end up getting that the speed that it's moving around the circle is 12.57 meters per second. I can now take this and combine it with the centripetal acceleration equation. So square this speed and divide it by 2, and you should have gotten about a little bit under 79 meters per second squared. All right, and here's the last one. So pause the video, work itself. I'm going to go in a second. So again, we have to do a little bit of extra work in order to find the speed. So they're telling us that it makes 10 circles in 5.3 seconds. So again, I could think about that proportion, and by definition, the period is the amount of time it takes per cycle. So if I get 5.3 seconds, 10 circles, let's say, I could set that equal to x seconds in 1 circle. So realistically, what I'm doing is taking the 5.3, dividing it by 10, and I end up getting 0.53. So I can take my velocity equation, use the period to be 0.53, and this time my speed is going to be 11.86 meters per second. Plug into my centripetal acceleration equation, and I end up getting 140.5 meters per second squared. And that's pretty much it when it comes to centripetal acceleration. You'll see what we're going to end up doing with this, but for the most part, I will point out that a lot of the stuff that we do in the circular motion isn't really going to change too much of what we've done in the past. If you recall when we talked about inclined planes, the inclined plane that I mentioned only really affected the initial FPD, taking the FG and splitting up into components. But once you got past that point, the inclined plane didn't play any other factor, and you could treat it like any other problem. It's going to be something very similar to here, where it just slightly changes one of the steps that we take, but we're still going to approach every single problem in this unit the same way, where we draw FBDs, do the F net equals MA, and everything like that. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.